Welcome back. Let's see, in the last session we have seen for a distortionless system what should be manual response and what should be phase response. The manual response should be flat, the phase response should be linear, then only we will say there is no distortion. And if you take RC coupled C amplifier, let's see what is manual response. Okay. Now let's see. This is what is your omega or frequency, and we are trying to plot your gain, magnitude, voltage gain, okay, for this. Now we know that I'm speaking. What about DC? For a DC, capacitor is open, open, open. This amplifier, RC coupled C amplifier, is not it is not amplifying DC signals. It is only amplifying AC signals, right? Therefore, for zero frequency there is no gain. You can say gain is zero. For zero frequency, gain is zero. Now, for low frequencies, right? Because for very low frequencies, this is almost open circuit, open circuit, open circuit. Then whatever signal you are applying, the low frequency signal, that is not going to input to the transistor. If the input signal is not going to input to the transistor, then it is not amplifying. Even though the partial signal is going, let us say 1% of VA is applied here, then that too with maximum feedback, because this is almost open circuit, with maximum negative feedback, whatever signal which is what is applied with minimum gain, whatever signal you got after minimum gain, the signal, it will be passed from here to here. Let us say 1% of this is, therefore I can say almost zero. But remember, as the signal frequency is increasing, slowly the capacitor will be shorted. This is also shorted, this is also shorted. Therefore, for low frequencies we will not have any gain, but as the signal frequency increases, remember the gain, that is what is increasing, and then at a particular frequency your gain will become constant. At what frequency? That is what people call it as your lower cutoff frequency. At lower cutoff frequency, because whatever impedance you have, I told you, right, this is what is, let us say Z1, then whatever input impedance you have, let us say that is Z2, then overall I can say this is Z1 and this is Z2, this is Z1 and this is Z2, right, and this is what your VI. Now the actual input what you are applying to your transistor, right, let us say this is what your VBE, therefore what is this? This is VBE, let us say this is short circuit, then what is this VBE? VBE or VB, let us say voltage at base, VB is equal to Z2 divided by Z1 plus Z2 into VI. Therefore if Z2 or Z1, the combination, therefore let us say Z1 is very much less than Z2 at least 10 times, then can I say that VB will be approximately equal to VI? Not necessarily physically short. The ratio Z2 Z1 combination, if Z1 is very much less than Z2, then I can say VB is approximately equal to VI, right? Because normally we say that capacitor acts as a short circuit only when frequency is infinity frequency is not required. For a given frequency, the Z1, Z2, if you see the ratio combination, then if VB, the voltage at this point is approximately equal to VI, you can treat it as short circuit only. Both are same only, right, indirectly. Then if this is what is the scenario, then you can take VB is approximately equal to VI. If VB is approximately equal to VI, then whatever signal you are giving, your signal is, your transistor is amplifying the signal with the gain what we calculated from common emitter configuration, which is nothing but, let us say, simplified model, then minus HFE into RL. Now RL is nothing but RC in parallel to RL, that is what your effective load, minus HFE into RL dash divided by HIE, that is what is our voltage gain, right? Then this is what is amplified, because this is also almost short circuit with respect in parallel to RE, we have to see this. Similarly, in combination to RC, we have to see how it is acting, right? Therefore, if you consider that your gain will be almost flat, assuming that at a given frequency, that is the lower cutoff frequency, these are all almost short circuit, then you can say this is what is our gain which we calculated from H parameter model, which is nothing but HFE into RL dash divided by HIE. This is what is our voltage gain, right? This is what is the voltage gain. Now, therefore, why the gain is changing? The gain is changing because of coupling capacitors. Now, but if you increase the frequency, yes, at a particular frequency onwards, your gain is what we are expecting. Yes, it is matching to H parameter model gain, because during AC analysis we don't bother about these capacitors. We will assume that they are short and then we will do it. But those capacitors are acting as a short circuit after signal frequency. After a certain frequency, then only you are getting gain, which is what is matching to H parameter model what we calculated. Now, at very high frequency means short for signal frequency ground CE amplifier. But remember, we have, I already explained, right, hybrid pi model. We have two capacitors, right? This is CD and this is CT. At very high frequency, maybe for your understanding, as I told you before, short, therefore your output is becoming input. Similarly, your output is becoming 0, therefore your output will be in between 0 to Vi because of Miller capacitors or because of BJT internal capacitances, because of which your high frequency gain will be falling. At very high frequency, as the signal frequency is increasing, slowly it is becoming short circuit. As it is becoming short circuit, basically it is connected to base bias. The CT is acting as a connected to base bias feedback resistor, due to which the gain will fall. When the gain is falling at a very high frequency, your gain will become 0 also, because of it will be in between 0 to Vi, therefore less than 1. Whatever may be, the gain is falling. Therefore, and people define, we know, right, this is what your flat portion, almost flat portion. Then there is something called 3 dB bandwidth. To define 3 dB bandwidth, this is what is defined with a lower cutoff frequency, and this is what is defined with higher cutoff frequency. What do you mean by 3 dB bandwidth? There are two types of bandwidth. One is absolute bandwidth, the frequency range in which the gain is absolutely flat. That is what is called absolute bandwidth. The frequency in which the gain is more than 50% of the maximum gain, or the power what you are delivering to the load is more than 50% of the maximum power what you are delivering to the load. In what frequency range you are doing that, that is what is called 3 dB bandwidth. Because when I say this is what is maximum power, let us say 100% max power, that is what is the power which you are delivering, then here the power whatever you deliver, right, definitely more than or equal to 50%. Here also more than 50%. But here in this portion the power will be less than 50%. Because the gain is falling. When gain is falling, right, the signal output peak to peak, for the same input signal peak to peak, the output signal peak to peak is reducing. Then your power what you are delivering to the load, that is what is decreasing. If the power which is what is less than 50% of the maximum power with the flat portion of the gain, that's why people call these two frequencies as half power points. Half power points. Exactly at F is equal to FL and FH, the power what you deliver to the load is 50% of maximum power. That's why people call them as half power points. Then this is what, if you say 1 by root 2, because when I speak about power, this is nothing but when I say voltage gain AV, this is what is voltage gain AV, let us say mod, right? Then this is what your gain, okay? Then this is nothing but AV by root 2. When I speak about voltage gain, that is nothing but voltage signal. Then what is your power? Power is nothing but square, V square by R. V square by R is nothing but AV square divided by 2. Therefore, whatever power you are getting, half power. That is what it is. Therefore, this is what is nothing but your bandwidth. And this is what is your gate. And this gain is called as, the gain whatever you are getting, right? This is what is called as mid-band gain. This is what is called as mid-band gain. Why it is called as mid-band gain? At low frequencies, gain is falling. At very high frequencies, gain is falling. Only in the mid-range of frequencies, your gain is almost flat, right? Above 50% of the maximum power to the load. Therefore, that is what people call it as mid-band gain. Whatever gain we calculated from H parameter model, right? Voltage gain, which is nothing but minus HFE into RL divided by HIE. That is true only for mid-band frequencies or mid-band input signal frequencies. Okay, take it. I'm just going with qualitative analysis only. I'm not explaining quantitative part, because to get FL, FH, we should have the transfer function of the circuit. It is like Bode plot. Tell me, how will you plot Bode plot? We should have transfer function, then S is equal to j omega, then find zeros, poles, then plot the frequency response, both magnitude response as well as phase response. That is nothing but Bode plot. How to get Bode plot for this? We should have transfer function. How will you get transfer function? We should have BJT internal circuit or equivalent circuit. What is BJT internal circuit? Where it is having CDN and CT, H parameter model failed to explain. For that we went for hybrid pi model. If you consider hybrid pi model where it has CDN and CT, then write input to output transfer function, then S is equal to j omega, then H of j omega, then plot, you will get it. But instead of going with mathematical analysis, directly I am saying qualitatively why gain is falling at low frequency. That is because of external coupling capacitor, and why gain is falling at very high frequency. Those are all due to BJT internal parameters. Therefore, if you ask me the gain fall, whatever you have here, right? Therefore, this is what is due to coupling capacitors. Coupling capacitors. What are they? CB, CE and CC. And this frequency response is due to, this is because of what? Due to BJT internal capacitances. Internal capacitances. What are they? Diffusion capacitance and transition capacitance. That is what it is. Qualitatively, I just explained. Therefore, we got the frequency response analysis. Sorry, magnitude response analysis. Because frequency response analysis is associated to magnitude response and phase response. I am just drawing magnitude response. Actually, it has frequency distortion. Your gain is not flat here. Your gain is not flat here. Your gain is almost flat only in this portion. In what portion you have gain which is almost constant, that is what is your mid-band gain, and that is what is your bandwidth. Okay, that's why every system is defined with bandwidth, because in that frequency range your gain is flat. Other than that mid-band gain or other than the bandwidth, we have frequency distortion. Frequency distortion is nothing but your gain is varying with respect to frequency. Therefore, this is what people call it as frequency distortion. Therefore, this is nothing but frequency distortion. Frequency distortion due to coupling capacitors. Here also frequency distortion due to BJT internal capacitors. I'll give you 2 more minutes. Then after that we will see the frequency response of multi-stage RC coupled CE amplifier. Okay. But before that I'll explain the limitation. I think the frequency response itself is saying, the plot itself is saying the limitation of the circuit. Done? Okay. Now write down limitation. Limitation of RC coupled CE amplifier. Even though we are saying this is best amplifier, right, from BJT amplifier, but still it is having limitation. See, best, finally best. Then again it is better with respect to something. Then improve it, it will become best with respect to that implementation, but maybe it is better with respect to something. Always, there is always comparison between one circuit to another circuit, or one advantage to, or one comparison to another comparison. Therefore, we are getting very good gain, but where? Mid-band gain. We are not getting gain for low frequencies. We are not getting gain at high frequencies, right? At least I am not expecting very high gain or high gain at higher frequencies. I don't want, let us say, high frequency signal processing. At least I want low frequency signal processing. Therefore, at least I want to amplify low frequency signals. But your RC coupled CE amplifier does not have low frequency signal amplification, right? That is the limitation. Okay, write down limitation. 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 What is the limitation? Limitation is nothing but it cannot amplify low frequency signals. Write down RC coupled CE amplifier. RC coupled CE amplifier. RC coupled CE amplifier cannot amplify. RC coupled CE amplifier cannot amplify. RC coupled CE amplifier cannot amplify low frequency signals. RC coupled CE amplifier cannot amplify low frequency signals. Cannot amplify. When I say amplify, with constant gain, it is having gain but gain varying. That is not said to be as amplification. Okay. RC coupled CE amplifier cannot amplify low frequency signals due to external coupling capacitors. Due to external coupling capacitors. Due to external coupling capacitors in bracket CB, CE and CC. CB, CE and CC. Okay. Write a note. Write a note. CB, the input, the coupling capacitor CB. Write down. Write a note. First point. Coupling capacitor CB. Coupling capacitor CB couples. I'm just explaining the functionality. Coupling capacitor CB couples input AC signal. Couples input AC signal. Couples input AC signal to couples input AC signal to to transistor input couples to transistor input about input DC bias voltage, about input DC bias voltage, about input DC bias voltage, about input DC bias voltage. Now second point, the coupling capacitor CE, the coupling capacitor CE, the coupling capacitor CE will bypass the feedback resistor RE. The coupling capacitor CE will bypass the coupling capacitor CE will bypass the feedback resistor RE for the feedback resistor RE, the feedback resistor RE for input AC signals, for input AC signals, for input AC signals. Therefore CE is helping, therefore CE is bypassing, therefore CE is bypassing negative feedback resistor, therefore CE is bypassing negative feedback resistor RE, therefore CE is bypassing negative feedback resistor RE during AC analysis, during AC analysis. Hence this is also called as bypass capacitor. Hence this is also called as bypass capacitor. Hence this is also called as bypass capacitor. Okay, coming to the third one, CC. The coupling capacitor CC, the coupling capacitor CC, the coupling capacitor CC blocks the DC voltage from transistor output. The coupling capacitor CC blocks, the coupling capacitor CC blocks the DC voltage, from transistor output. The coupling capacitor CC blocks the DC voltage from transistor output and passes only AC signal, and passes only AC signal, and passes only AC signal to the load, and passes only AC signal to the load. Hence this capacitor is also called as, blocking capacitor. Hence this capacitor is also called as blocking capacitor. Hence this capacitor is also called as blocking capacitor. Okay, this is done. Now if you take multi-stage amplifiers, what is frequency response? Just listen, don't write. This is RC coupled CE amplifier. having frequency response like this. Now if you give it to one more RC coupled C amplifier, then what is our frequency response? Therefore it is also having the same frequency response. Therefore similar RC coupled C amplifiers. Now what is overall frequency response? Therefore remember that mid-band gain whatever you have, right? Let us represent mid-band gain here AV1, then here the mid-band gain of RC coupled amplifier AV2. Then if you ask me what is frequency response of RC coupled C amplifier, right? Then just listen. If you take single stage amplifier frequency response, this is what is our single stage amplifier frequency response, right? Then if you take two stage amplifier frequency response, it will be having now if you take single stage amplifier frequency response and this is what is the gain, let us say this is what is the gain, this is what is AV1 or AV2, AV1 or AV2, both are having same gains, and this is nothing but your AV1 by root 2 or AV2 by root 2, and this is what is our lower cutoff frequency FL, and this is what is our higher cutoff frequency FH. But if you have two stages of RC coupled amplifier, then you are having gain, the gain is increased. Therefore now what is the gain? AV1 into AV2. Then if you ask me the bandwidth, right? The bandwidth of two stage amplifier will decrease. Your gain is increasing but the bandwidth will decrease. AV1 into AV2 divided by root 2. Okay, now this is what is our new lower cutoff frequency, let us say FL star, and this is what is our new higher cutoff frequency, and this is nothing but your bandwidth, new bandwidth, let me say bandwidth star, and this is what is the earlier bandwidth what you have, this is your bandwidth, is equal to FH minus FL. Here this is FH star minus FL star. Now I can give you the relationship between FL star to FL. I am not deriving, but that is what is derived using hybrid BJT hybrid pi model. Okay, I told you, right, transfer function and then transfer function, then we can calculate that, which is again it is associated with huge mathematical analysis, right? But it is easy anyway that we used to do or we did in our engineering. Okay, fine. If you know the methodology, you can do it, and then you can refer back and then you can do it. But ultimately the concept is important. Let's see, and then problems whatever you are getting related to qualitative analysis, not quantitative analysis. Okay. Now if you ask me what is FL star, your FL star is increasing, right? With respect to FL, there are problems. FL, FH, the values are given. Asking for FL star, FH star, if you have two stages or three stages, we don't know, right? Let's see. FL star is equal to FL divided by 2 to the power of 1 by n minus 1, where n is nothing but number of stages. Similarly, FH star is equal to FH into 2 to the power of 1 by n minus 1, where n is equal to number of stages in cascade stages. What do you mean by cascade stages? Output of first stage is input to next stage. Therefore, they are in cascade or they are in series from input to output. If that is what is the scenario, let us say n is equal to 1 means single stage. N is equal to 1 means 2 to the power 1 by 1, 2, 2 minus 1, 1. Therefore, FL star is nothing but FL. If n is equal to 2, 1 by 2, root 2 minus 1, 1.414 minus 1, root 0.4. Root 0.4 is less than 1. FL divided by less than 1, more than FL. More than FL is nothing but your FL star. Similarly, FH star, this is less than 1 means less than FH, less than FH. Okay. Therefore, n you can take number of stages. If I say 3 stages, n is equal to 3, then this is what is the bandwidth. Okay. I am not deriving. You can take these formulae as granted. That is from hybrid pi model of your BJT and then having transfer function and then doing all these things. Okay. Take it. But here what I want to say, the gain is increased but bandwidth is decreased. Therefore, your gain is inversely proportional to bandwidth. When I say bandwidth, default 3 dB bandwidth, not absolute bandwidth. For all the systems, typically people define 3 dB bandwidth. For all the signals like voice signal, audio signal, video signal, right? For all the signals people define absolute bandwidth. Okay, because we don't want to miss any frequency component, right? All the frequency components should be present. Therefore, people take absolute bandwidth for the signals and 3 dB bandwidth for the systems. With this I can say BJT amplifiers are over. From next session onwards, we will see the workbook problems and the test problems related to chapter 2. Whatever theory we covered till now, we need to apply the theory or the formulae while solving the problems. Okay. Now you will get real confidence after solving the problems. How to apply the theory, how to solve the problems, right? You will get to know. Maybe it will take a couple of sessions to see the problems related to chapter 2, basically BJT amplifiers. When I say gain here, AC gain, bandwidth 3 dB bandwidth of the system. See, one point I can explain qualitatively. Here the gain raise, right, or the gain change for single stage amplifier is something, but the gain change for 2 stage amplifier is faster. I can explain using Bode plot. If you have one stage, let us say it is defined with 0 pole, then one stage 1 0, therefore 20 dB per decade. 2 stages 2 zeros, 40 dB per decade. Therefore that's why the slope is now different. If I say this is 20 dB per decade, this is 40 dB per decade. Done? Now coming back to this, you see gain fall, that is because of a pole. Let us say it is having a pole, it is one pole having one pole, 20 dB minus 20 dB per decade. 2 stages, therefore between input output now 2 poles. Therefore, you can say minus 40 dB per decade. I'm just giving example, okay? Minus 40 dB per decade. That's why the slope of this is steeper than the slope of single stage amplifier. That is important, okay? But if you observe, even though bandwidth is lesser, the bandwidth is lesser for 2 stages, but if you take at a given frequency, if you take single stage amplifier having some gain, But the gain is more, but the gain is varying. Because gain is varying, people are taking that, don't take that frequency, because we want gain to be flat. The gain value is also important, and the gain should not vary with respect to frequency. That's where bandwidth is coming to picture. Okay. If gain is increasing, then your bandwidth will decrease. That is what is the typical relation people say. Or people say gain into bandwidth is nothing but constant. If you take your op amp, the gain into bandwidth of your open loop op amp is nothing but unity gain frequency. That is what we are going to see later. Or transition frequency, FT. That part I will explain later. Okay. Let me stop now. Then we will continue in the next session. We will see the workbook problems. Okay. Try to carry the workbook. We will see the problems. Thank you.